This week we're going to cover igneous rocks, but I thought I'd start out with a quick little video that explains where igneous rocks come from. So this week we'll focus on igneous rocks as a whole, but kind of break it down a little bit. There'll be some more focus on what are called plutonic rocks. Those are rocks that cool inside the earth. And next week we'll focus a little more on volcanic rocks. Those are ones that make it to the surface. So we'll do some volcano stuff next week. But this still applies to both those types of igneous rocks. And remember, an igneous rock is anything that's cooling from molten rock, crystallizes. So what we want to think about when we think about where do these rocks come from, and you have some of this information already. So it's the idea of why is not the earth all molten? Or is it? Right? So we don't want to have the misconception that as we drill down into the earth, we reach this part of the earth that is a liquid. Now, we're not talking about the core here. So we know that there's a liquid outer core and a solid inner core. That is a different material than the mantle. So when we drill down into the earth, we don't end up getting into this liquid magma that exists everywhere at depth. And so it only happens in a couple places. So you guys know kind of this information that I'm showing you on the screen here, right? We know core, mantle, crust is the general composition if we were to break down the interior of the earth. You know some plate tectonic stuff. We know that there is a brittle surface here that's in motion. They're colliding with each other. These collisions occur at plate boundaries. There's different types of plate boundaries. We have earthquakes that happen here and volcanoes, though volcanoes don't happen everywhere. So we want to kind of understand why, because of course to make a volcano, we need a source of magma, some molten rock. So we know that plate tectonics gives us some of these molten materials, though they don't occur at all the boundaries. So it's super hot when we drill down or go down into the earth, because of course we can't drill super deep, but we know that it's really hot down there. So why isn't the earth full of magma? It's at temperatures where most materials, rocks, minerals, should be molten, but we don't see that happening. What we kind of see when we look at the earth, so here's a crude cross-section of the earth where the blue will be the core, both inner and outer. The white line will be the crust and everything else will be mantle. So when we look for where do we see magma, molten rock at depth, this is kind of what we see. There's these little pockets that show up very near the surface around the globe, and they don't show up really deep inside the earth, just near the surface here. So why are they happening there? One of the things we want to think about is why do rocks melt in the first place? So what's causing the molten rock to occur at those places? And most people can say, okay, I get it. We add some heat, so there must be some extra heat there. Okay, and that's a good reason why rocks melt. We know that we can change the temperature. So that's one possibility. The other two aren't quite as clear, but we can change the pressure. So remember, as we go down into the earth, the heat is increasing, and we would suspect that we should see some molten rock down there. But pressure is also increasing. And so think of pressure as fighting against heat, right? Heat wants to excite the molecules and move them apart so that they expand and they change from a solid to a liquid. Well, pressure is doing just the opposite. It's crushing those molecules together, pushing them together, keeping them a solid. So there's a battle as we go down into the earth between heat and pressure. And so most of the time pressure is winning this battle and keeping things a solid. Now the other way we can make rocks melt is we can change its composition. And so there are some parts of minerals that are in the chemical structure that have weak bonds that can be broken, and we can move those materials around and introduce them to other minerals, and if they bond to the new mineral, it would create a new mineral. And that new mineral would have different properties. One might be a lower melting temperature, which would then allow that mineral or rock to begin to melt. So when we look inside the earth, we know that as we go down into the earth, we see a temperature increase. So I'm going to blaze through this pretty quickly, so don't focus too much on this, but as we zoom down into the earth, we can see that temperature is increasing, and so is pressure. So what I've kind of drawn for you is what's called the geothermal gradient. It's different in different locations. It's not always perfectly the same, but You know, in places we can get kind of a 20 degrees Celsius change for every kilometer we go down into the earth. But we would also say that, well, as we go down into the earth, if things are the same composition, there should be some melting temperature, that you keep going deeper, 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 finally, boom, you melt the stuff. But we just said that pressure is changing the melting temperature. It's making it higher by not allowing it to melt. So we kind of get this little slanted line like this. And so in order to make our rocks melt just from being buried, we have to do something to push them past that green line, if you will. And so if I have a couple points like this, if I want number 1 to melt, I'm going to have to do something. And the only thing I can really do at this depth is I must add a ton of heat. If I could do that, for some reason, right, I could push that rock to the right, it would cross the melting temperature there, and I could start to melt the rock at that depth. If I'm at number 2, I can do something different. Now, I could also increase heat there and move it to the right. But if I change its pressure by decreasing it, if I could move number 2, the rock there, up to a different depth, a shallower depth where the pressure isn't as high, the melting temperature would be different. It would be lower, and I could cause that to melt. And so we got to either move things or heat things. So we got to figure out where we can see that. The last thing really quick about this is when we have water in the magma, and so we can get water that's in the magma dissolved in there, the more water there is, the lower the melting temperature. So if I could introduce some water into the magma, you can see that the sample number 2 there would melt without me doing anything besides introducing water. This is our change in composition story. So how do we do all this? Let me show you my exciting graphic there. These are the 3 ways that we're melting things: alter, reduce pressure, or add heat. Okay? So how do we move things around? Well, we know that there is convection occurring inside the mantle. And so that is this idea that material changes density as it gets hotter or colder. And so this little Bunsen burner example here is that when you put water on a stove, let's say, you start to get what are called convection currents. Near the source, the heat source, the water there is hotter than the water that's at the surface of my container, and so that water is less dense. So it starts to rise because it's less dense than the colder stuff that's above it. As it rises up toward the surface, it pushes the cold stuff out of the way, which then sinks, gets hot, and the cycle repeats, and you get these little cells here that kind of migrate like in this pattern here. Now, they're not always that pretty, but we're trying to just make it simple for us. And this is one of the things that is moving the plates around. As my magma, don't use that term, bad, as the mantle is moving. Now, it's a solid here. I misspoke, right? We don't want to use the term magma when we're talking about that yet. So we're rising up here and moving this way. It's dragging a brittle lithosphere with it, and this is helping move the plates here. Okay, all right, so as a very simplified kind of diagram, we would say here's the mantle and there's some convection happening here. There are convection cells that have been set up here. Now, this is a super simplistic version. There's probably multiple layers of convection happening inside the earth, and of course they're not all neat and pretty like this, but to show you the idea that the mantle here near the core is hotter than the mantle up here, and so this is less dense than this. It starts to rise up, it pushes the cold stuff out of the way, which eventually sinks back down, gets hot, rises up, and we get these patterns that form here. So look, here's one way that I can move material. We said that if we change the pressure by moving a rock from here to here, I can cause it to melt. And voila, we do that through convection. And so when we look at some plate boundaries, we see that we have the mantles rising up here. Why? It is hotter down here than it is up here, less dense. Think of the story Hot Air Rises. Why? It is less dense than cold air. And so it happens too for our mantle. It rises up here, it runs into this cold, brittle lithosphere, and so it can't go anywhere, so it splits and moves away, and eventually it sinks back down. Okay, so what we see at divergent plate boundaries is that we are decompressing the mantle here, so that we have decompression melting. All that's saying is we're reducing the pressure. So as the mantle rises up, the pressure drops. Now, I get it, the temperature is also dropping, but not as significantly as the pressure, right? The material here is holding on to the heat, so I rise it up, and finally I reach a point where pressure loses and temperature finally wins, and we start to partially melt the mantle. Everything just doesn't go poof and melt instantly, because remember, the mantle is made of different minerals, each having their own melting temperature. So we start to melt the minerals in this material, the mantle, that has the lowest melting temperature. So not everything in the mantle melts, only certain minerals in there, but they become liquid. Liquid is less dense than the solid, and once again, I have movement. So my liquid starts to rise up and collect, and it forms some chambers, which eventually at this location where I'm ripping the crust apart, I have magma available to come to the surface and fill that gap and form new crust. So at divergent boundaries, we get decompression melting. This is what's driving the melting here. This is why there's magma at this location. Okay? If we look at convergent boundaries, the other place that we get volcanism. Why? Well, look, we take this plate here and we subduct it. We need subduction, that process, to initiate melting at depth. Do we get melting over here? No, there's no process to cause magma to form here. Divergent boundaries, there is a process, so I can get volcanism there. Here, this plate, which has been hanging out for 200 million years because it formed way off to the left and has been slowly moving along, has lots of minerals that are sitting here that are what are called hydrous minerals. They have a lot of water in their molecular structure. And I'm taking all those minerals and pushing them deep inside the earth. And as the temperature rises, it causes the bonds that hold the water there to break. They become mobile and they mix with some of the minerals that exist here in the mantle. Here we can have a composition change. The addition of water can cause the rocks to change properties, because remember, I changed the chemical composition, I have changed my mineral, and now it has a lower melting temperature. And so before the water, it's a solid, happy, hanging out at this depth and pressure, right, this temperature and pressure, but I add water, change some parts of my mineral, now it has a lower melting temperature, it can't stay a solid at that depth and pressure, and it starts to melt. Once again, my liquid, less dense than my solid, what happens? It's mobile. It starts to rise up here. And so this liquid, this magma now can rise up and move all the way through the crust and create volcanoes up here. It can also kind of pool here at the base of the crust, depending on some properties of the crust, and add some heat here and start to partially melt my continental crust here. So I get both things happening. But the big thing is this change in composition, which is initiating the melting here. Subduction is allowing the melting to start. So I need subduction to make magma, so then I can make volcanoes. And the only other place we really see that is at hot spots. So not a plate boundary, but I have decompression melting happening here. Why? Because I have a heat source that's causing the mantle to be hotter at depth. And so I have a rising plume, because the hotter mantle is less dense than the colder mantle, so it rises up and it impacts the lithosphere here, which could be continental or it could be oceanic. It can break through the crust here and cause volcanism at certain locations that are not associated with the plate boundary. Okay? And so here's what I want you to remember from all this. Let me bust all these out here. So look, what is magma? Molten rock inside the earth. How do we get magma? We either have to increase the temperature locally, we have to decrease the pressure, or we have to change the composition. And so the increased temperature is usually some other magma body interacting with some other rock. The decompression stuff is the moving mantle, rising from deep inside the earth, right, making it to the surface is changing the pressure, reducing it, which can allow it to melt. And the changing composition is mostly associated with this subduction idea, that we're causing the introduction of fluids, water, into the rocks at depth, which is changing some of their properties, causing them to melt at that location without having to move them. Then they become mobile and move up. So why is all this happening? Right, convection of the mantle is causing motion, which is causing plate tectonics. So these two are working hand in hand. I have rising material, which is causing melting. I have collisions of plates, which can lead to subduction, which is causing melting. And so what are boundaries that we've talked about before? Divergent, decompression. Convergent, we have this change in composition from subduction. Look, if there's no subduction, there's no magma formation. This is why we argue that when two continental plates collide and subduction is no longer happening, you can't get volcanism there because there's no mechanism to cause magma to form at depth. Same with the transform boundary. You don't see that here either. Why? Because there's no subduction and there's no pulling apart of the crust here because decompression. So at transform boundaries, there shouldn't be any volcanic activity because there's no mechanism for causing magma to form at depth. Okay, so just remember that magma is not everywhere inside the Earth. It's at these specific locations. This is why plate tectonic theory is very helpful, because it explains why we get volcanoes or volcanic activity at different places and not just everywhere. It's specific. It's specific to divergent plate boundaries. It's specific to subduction zones, and it's specific to hotspots. Okay, hopefully that helps, and then the next little lecture we'll get into igneous rocks themselves.